Hey everyone, how goes it? Welcome back to Computer Science 552 Game Development. Today, we will be discussing the essentials of interactive movement, or how to get moving. Within our game production process, we're going to focus primarily on game development. Within that process, we now focus directly on the role of the programmer, and focus directly on concepts related to design and implementing game code. Conceptually speaking, a game is just like any other kind of software. It acquires input, processes the input, and outputs a result. Moving game objects is very common in most games. For example, user presses the up button and the player moves. Breaking this down, acquiring the input is user presses the up button. Processing the input is increase the player's Y coordinate. And the output is draw the player's game object moving up. This can also be described using the game loop pattern. We understand that time is a critical factor in all games. Games constantly need to provide feedback to the player by handling events, updating game objects, and drawing the results to the screen. The game loop pattern describes the common sequence of these steps. Step 1, handle the events. Step 2, update the data. Step 3, draw the results. This pattern decouples the progression of game time from user input and processor speed. The game loop pattern helps us to organize the game's behaviors into common occurrences. As discussed, each game loop iteration progresses the game. The event step involves gathering information about occurrences that have happened since the last game loop iteration and then applying the necessary actions related to it. User input, collision detection, message handling are all events. The update step modifies the data periodically based on these previous events and previous data. Moving the player, destroying an asteroid, collecting a coin are all updates. The draw step simply draws the results of the update. In games, a frame is an abstract unit of time between each game loop iteration. Typically, one game loop iteration is equal to one frame, which is equal to one sequence iteration. Each frame progresses the game. In real-time games, this means that the frame progression matches closely to actual time. Sports games, real-time strategies, platformers, etc. are real-time games. Turn-based games mean that the frame progresses only when it meets a certain criteria, taking turns like in RPGs or chess. Frames per second or FPS is a way to measure the speed of a real-time game's progression. This is called the game's frame rate, and a game that runs 60 frames per second performs 60 game loop iterations for all game objects for all components 60 times every second. Practical time efficiency of code is a very high priority in achieving good frame rate. As previously mentioned, Game Engine is a software framework for developing games. It includes necessary software libraries and supporting programs. It typically contains graphics libraries, physics engines, input managers, audio managers, and message passing capabilities. As mentioned, game engines are not required for making games, but they can assist in speeding up development. More often, the game engine can be considered to be the game system. Also, the game engine is the code which runs or drives the game. It's in charge of calling the functions related to the game loop pattern. These functions can be considered to be event messages that are sent to each game object, then delegated to each component. Programming interfaces provided by the game engine are used to create the components. In relation to the game loop, a game engine commonly provides a means to utilize the game loop through managers, provided components, and programming interfaces. Movement or motion describes how an object changes position, rotation, and scale over time. Interactive movement requires an input from the player to change a game object's position. Game engines provide a time manager to call functions related to the game loop, an input manager to acquire the player's input, transform to maintain and update the player's position, and a sprite to draw the game object. Game engines must periodically update every component for every current game object within the scene. This is based on the game loop pattern. and this is measured by frames per second. A time manager allows a developer convenient access to a game's clock. Some important properties of a time manager is the current time. This is the real time or the time since the game started. Also, delta time is the time between the past and current update calls. The delta time may be frequently used to convert from velocities to positions in transformation calculations. This is important to avoid strange movement behaviors on different platforms on different architectures. A time manager also allows the developer convenient modifications of the game's clock. The time scale, or speed, property can be used to either speed up, slow down, or stop a game entirely. This directly affects when the update calls occur. Setting the time scale to 0 will result in no updates, so the game will be effectively stopped. Quick nifty tip: setting the time scale to 0 can be a good way to stop or pause a game. In Unity, the class time provides a reference to the time manager. Some important static properties of this is delta time, the amount of time that has elapsed since the last update call. In other words, the change in time. Timescale, a percentage representing the scale of time and the speed of the update calls. The value 1 represents 100%, meaning as close to real time as possible. 0 means to stop and no update calls will occur. Quick nifty tip: delta time is really good when calculating movements from velocities. Multiplying meters per second by delta time, or seconds, results in just meters. This assists in constraining the updates to work similarly on all systems. Instead of updates can occur a little quicker, thus they move a little faster on some systems. We can best see this by looking back at a previous example. We saw how to create a quick script which caused the ball to move and reflect. Looking closer at the scripts, we can see the statement transform.translate transform.write times speed times time.delta time. We can see that time.delta time is used here. The change in time from one frame to another is the delta time. It's the measure of real time between each update. We see that this value is multiplied together with a direction vector right and a speed. This is done so the game object will be repositioned or translated to a new position. However, translation is about setting positions and is not concerned with speed. Speed describes the change in position with respect to time, so we need to remember how to convert from speed to position. When it comes to motion, we have learned in our studies of physics that it is important to keep units in mind. Position is in meters. Speed or velocity is in meters per second. Acceleration is meters per second or meters per second squared. We note that velocity describes a speed with a direction. For our example, we are going to use these terms speed and velocity interchangeably. In relation to position, velocity, and acceleration, delta time s can be used to convert from speed to position for translations. For example, we can consider that the position n plus 1, in other words the next position, is just equal to the current position n plus the speed multiplied by delta time. The position at the next time step is just adding together the position at this time step to the speed by some amount of time. This can be very important to use in the case that some software can be run faster on other machines. If the movement is based on the game loop's frequency, which is based on the CPU speed, then it is not real time. And in fact, faster computers will move the game objects faster, and slower computers will move them slower. In other words, they'll behave differently. Once again, we revisit this example and we're going to create two different versions, one that uses time.delta time and one that does not. We can see on one machine, the effects are noticeable. This was clearly going to happen as the formula has changed from one to the other, so this is not that interesting. The use of delta time is more obvious when we see how it behaves on multiple devices. After building each one, we can see the side-by-side effects. This was built using delta time, and we can see that the game looks like it functions the same way across these two machines. Now, we see these machines are running the same code that does not use delta time. One of the machines is executing the code slightly faster, which means the ball moves a little quicker. This is not great, as we need some consistency across all platforms. Using delta time helps conform the motion as closely to real time as possible, so that the machine's hardware does not change how the game is played. If our goal is interactive movement, then our next step needs to be to go over input. Most game engines provide a way to facilitate common forms of input via input managers or input systems. From these, input can be accessed either directly or indirectly. Direct input is raw input from a specific device, and it's considered to be very fast. Indirect input is also called virtual input. This is interpreted input from one or many different devices, and is considered to be slightly slower. While direct input is faster, indirect input is generally preferred for most game development. This also allows variety of different input devices to be interpreted in the game code as a single action. Input managers or input systems set up the connections from devices to the input that is interpreted as the action and its output. This is an example of the command pattern in software engineering. This is very ideal for multi-platform game development, as we do not need to worry about specifically implementing each type of input. All we need to do is to set it up in the input manager. The input manager can be used by components to implement the game's operational rules. Unity features either an input manager or an input system. The input manager is the default means to acquire input. The input system is a newer feature that is not natively built into all Unity projects yet. The input manager can be found in the project settings, going to Toolbar, Edit, Project Settings, Input Manager. This is where all the names of the virtual buttons and axes are found and defined. In Unity, the class input is a reference to the input manager. Some very useful static functions are getAxis. This returns a float value from -1 to 1, representing the current state of a virtual axis. getButton returns true on every frame as long as the virtual button is pressed. This is really good for press and hold actions. getButtonDown returns true on the first frame that the user presses the virtual button. This is really good for if you need to press it once, then release, then press it again actions. One thing to note that each of these functions require a string name, which corresponds to the button or axis established in the input manager. Now, we can see how to put this all together. Using the input manager, we can map the player's left paddle to W and S, and the right player's paddle to the up arrow and down arrow. Looking over at the editor, we can see the left player's game object has the move script. Looking into that script, we see how the movement works based on the vertical axis. We also see how the movement is based on delta time. So if we were to build this game, it would work the same way on every platform. We need to visualize the movement, so we need a way to graphically represent the game objects. A sprite is a 2D visual asset that is layered on top of background images or other sprites. These can be considered bitmaps or textures. They are also active entities that can be moved within the game space. In a game engine that supports 2D, sprites are also components that can be primarily used for drawing. It holds all the data related to the image, and it works alongside the transformation component to position, rotate, and scale the image. In Unity, the Sprite class is used for drawing 2D bitmap images, or Texture 2D. You attach this to a game object by assigning a 2D image from the project's resources. Some very useful properties is texture, the reference to the Texture 2D bitmap image. Sprite importers are typically provided by game engines. 2D bitmap images or textures need to be processed in order to work with the game. Importers handle common processing so these assets can be quickly utilized. Unity's importers can be used for different types of sprites. Single 2D images, user interfaces, multiple or animated 2D sprites. Sprites and animation will be discussed in the future. Now, we can enhance the experience by replacing the placeholder graphics with a couple of sprites. All we need to do is take the sprites from our resources and apply them to our scripts. We can do this for the rest of them, and then we can get something that looks like this. Now, we can start seeing how this is coming together. Looking ahead a little bit, rendering is the term commonly used when discussing drawing 3D meshes onto a screen. Game engines that support 3D also provide components that handle rendering a 3D mesh. There will be more details regarding how these work in the future. In this lecture, we've discussed the essentials of interactive movement. Now that we understand how to get input and how to use the time manager, let's get moving. And with all that being said, I'll see you next time.